Hello everyone, welcome to the final lecture of this fifth week. We are discussing the course on analog meters, which is the second module of the course measurement and instrumentation, and this is the 20th lecture of this particular module. Today we are going to discuss a new instrument, which is rectifier instruments. This is as per our promise in the previous class. We have discussed that we'll talk about this new variety of instrument. Rectifier instruments are in fact one of the few kind of instruments which uses electronic devices or electronic component along with the electrical component. Okay. Till now what we have seen is mostly you have the equipments or instruments which are either made up of certain electrical components or you have some mechanical component for deflection and other things. Here for the first time we are bringing the electronic component. Please note that when I am saying electronic component, what I mean to say is basically the introduction of semiconductor device in a analog instrument. Okay. So till now we have not introduced any semiconductor device. Okay. And in particular in the semiconductor device also now we are talking about diodes. Okay. So the rectifiers that we are going to or the rectifier instruments that we are going to discuss utilizes diode. It can be one diode, it can be multiple diodes in certain arrangement. Okay. So that rectification can be achieved. Okay. And let's see the configuration of these instruments to understand it in better way. Okay. So the rectifier instruments are a type of AC measuring instrument that uses rectifying element. So this is in particular uses to convert alternating current signal into a unidirectional signal. So what you are doing is you are not directly measuring the AC signal, but what you are doing is you are basically doing the measurement in indirect way. Means that you are using a AC signal, okay, converting that into a DC signal by using a rectifier, and then measure this DC voltage or say DC current, and then you comment on the measurement value of the AC signal. Okay. So this is an indirect way of measurement. Okay. So what we are doing with the rectifier instrument is we are converting the alternating signal or AC signal into a DC signal. Okay. And after this step, the resulting DC is measured by any DC responsive tool like a PMMC meter. Okay. And the calibrated to indicate the value of original AC value or original AC quantity, and this will be the RMS value, because you cannot show any other value or instant value. It's basically what you are talking about is the RMS value. Okay. This particular method of indirect measurement of AC signal is very attractive because PMMC instrument has higher sensitivity if you compare it to the electrodynamometer type or any other instrument like say moving iron instruments. Okay. So what you are doing is in conjugation with a rectifier, you are using a PMMC tool to measure a AC signal. Okay. So these rectifier instruments are suited for measurement on various communication circuits and for other light current work where the voltage is very low and the resistances which are under measurement is very high. Okay. So for those cases you basically deploy this rectifier kind of instrument. Okay. So for accurate voltage measurement, the current drawn by the voltmeter must be strictly limited to minimize any kind of loading effect that we have seen. The loading effect that we are talking about is in connection with the circuit in which we are trying to measure the voltage, or say a component across which we are trying to measure voltage. Okay. So the whatever analog tool you are using, be it's a electrodynamometer kind of tool or say PMMC kind of tool, you have to ensure that the analog meter itself do not overload or say do not load basically the circuit along which you are trying to measure the voltage. Okay. And we have seen in previous classes also that in practical application the voltage input current, the voltmeter input current is typically as small as possible, but less than 1 milliamp for sure. Okay. So excessive meter current can alter the circuit operating condition. Basically, it is loading the circuit. If it is drawing more current, okay, means that this will definitely lead to measurement error. Okay. So, rectifier type voltmeters are very much suitable for such application because it will not overload, it will not have this loading effect in a circuit wherever it is being corrected because of their high input sensitivity. Basically, if you see these instruments, the rectifier kind of instrument has high sensitivity of the order of say 1000 ohm per volt to even as high as 2000 ohm per volt. Okay. So, this kind of sensitivity if your system has or your analog meter has, okay, you can be ensured that low current consumption is possible. Okay. So, your voltmeter is not drawing very high current. Okay. So, these kind of instruments are very suitable. That is why I mentioned for when you are dealing with very low voltages or the resistances are very high. Okay. The principle of operation is very simple as we have understood. The AC quantity that is under measurement, okay, first you have to convert this to DC, okay, and then measure this DC using a DC instrument, preferably by PMMs. Okay. So, if you see, this is a typical structure of or stages of measurement. You have AC signal, you had a rectifier. This will give you a pulsating DC. Okay. So, you have pulsating DC like this, okay, or say even like this. Okay. And then you have your meter which is measuring this pulsating DC value. Okay. So, this PMMC instrument, we know that it can only measure DC. Okay. So, a rectifier is must. So, rectifier will convert this AC signal which was entering into this rectifier to a pulsating DC value. The average value of the rectified current basically produces the deflection. Okay. The scale is calibrated to indicate the RMS value of the AC, and the rectifier instruments indirectly measure the AC by converting these values into DC value. Okay. So, the working can be explained simply by understanding these three steps. The first is the AC input, second is the rectification process, and third is the measurement of the pulsating DC with the PMMC instrument. Okay. So, let us try to understand these three stages. Okay. The first is the AC input. Okay. AC voltage or current, whatever you want to measure, is applied to the instrument terminals through the rectifier junctions. Okay. And this AC signal of course cannot directly operate the PMMC instrument, and that is why these rectifications or the rectifier is in place. Okay. The rectifier circuit will depend on what is the configuration of diodes you are using or how many diodes you are using. Okay. So, if you are using only one diode, basically you must have a half wave rectifier. So, when I say half wave rectifier, what you are doing is only half cycle of the AC signal is used, and for the second cycle you will not have any output. We will see this in little detail. Okay. And if you have more than one diode, you may have full wave rectifier, okay, where both half cycles of the AC signal is used. Okay. This full wave rectifiers come in different configuration. You can have center tapped diode configuration or bridge type rectifier. I will recommend that you also go through some courses where you can find a good discussion on rectifiers. Okay. Since we are considering this particular part in a bigger course on instrumentation, we may not be able to justice with the rectifier part. So, I will suggest that you follow some good semiconductor device book where you can basically study more about the rectifiers, and if you know it well and good, and if you do not, and even if you are not going to study a semiconductor device book, or if you are not willing to do so, I think this discussion will have sufficient information about all these ways of rectification. Okay. So, two things we have learnt. One is half wave rectifier and another is full wave rectifier. Half wave rectifier will have only one diode component and will only be able to rectify half cycle of a AC signal. Okay. And when you can utilize both half of the cycle, okay, means you are talking about full wave rectifier, and this full wave rectifier comes in two different configuration. One is the bridge type configuration where diodes are placed, or 4 diodes are placed in a bridge configuration. okay, and then you have center tap diode configuration where you have two diodes placed in such a way that it utilizes both half cycles of the rectifier, okay. The rectifier converts AC into pulsating DC as we want in the second stage, and the third stage was the measurement by the PMMC instrument, and the rectified DC we are ensuring that will only flow through the PMMC instrument, okay. And due to interaction between this DC, okay, magnetic fields of permanent magnet and current carrying coil similar to any other DC measurement, you will have a deflection torque, and the measurement can be done, okay. So the deflection is basically proportional to I average, where I average is the average value of the rectified current, fine. We know that the PMMC instruments respond to average value. The instrument scale is calibrated in RMS value of AC, assuming a sinusoidal waveform, okay. So ideal rectifying element will have a unique current voltage relationship as shown over here, okay. The relationship shown over here is, as I have mentioned, is ideal, okay, and is linear in the forward direction while there is no current flowing in the backward direction. So you do not have in a proper rectifier, so you have say a diode, okay, I'm talking about ideal rectifier, okay. Now I am trying to pass AC signal, okay. Ideally this diode should offer a zero resistance, okay, or say minimum resistance, so that this signal is appearing at the output, okay, and in the reverse condition it should provide maximum resistance so that it does not cross through, alright. So this is what we want to say for the ideal condition, okay. The relationship for this case, for this shown case, is linear in the forward direction for the current and voltages, okay, while there is no current in the backward direction, okay. This means that the rectifier resistance is constant in the forward direction, however it is infinite in the reverse direction, means it is acting as a open circuit, right. Now this is a very idealistic condition which is not possible, okay. In practice the rectifiers are nonlinear devices, okay, and at lower value of the forward voltage the rectifier operates in the nonlinear part of its characteristic curve, and for low value of current the resistance decreases rapidly as the current is increased as shown over here, okay. When reverse voltage is applied, current is not zero but has a small finite value. You cannot expect it to be zero, as this concept is coming from semiconductor device physics, okay. I will suggest that you learn about a PN junction, what is depletion width, how electron and holes make, using the movement of electron and hole you create a junction, and how this junction behave, means when I say junction I want to say a PN junction right now, how it behaves when it is forward bias, when it is reverse bias, okay. So when I am using a term reverse voltage, I am actually reversing the biasing potential at the junction, okay. So when reverse voltage is applied, current is not zero, ideally it should have been zero, okay, but it has a small finite value, alright. So for a given voltage the forward current is very large, it may be several times of the backward current, okay. However, what we can understood from these discussions that simply the resistance of a rectifying element is not constant, okay, but it is varying with current, okay, and that is what a typical diode's characteristic is, okay. So you can have a different type of rectifiers because depending on what cycle it is using, okay. You can have half wave rectifier and full wave rectifier, and bridge rectifier is, I am not calling it a different kind of rectifier, but again it is also a full wave kind of rectifier, and this is a typical circuit arrangement for these three different instruments based on three different rectifiers. This is half wave rectifier based instrument, this is full wave rectifier based instrument, and this is a bridge rectifier based analog instrument, okay. So let's see them in very brief, okay. So half wave rectifier, we have seen from the initial time of this lecture that it utilizes only one diode, as you can see from the figure, okay, and it allows current to flow during only one half cycle of the AC input, okay. So say for example you are trying to pass a sinusoidal wave, okay, say, so what it will do is, till say this diode start conducting at say 0.7 volt, ideally we are considering at 0 volt, okay. So if I am considering for the time being at 0 volt, that when the voltage is rising from 0 to say certain positive value, okay, the input will follow the output, okay, and you will have again this kind of output, okay. However, in the negative cycle, okay, what you have is, say this is my diode and this is the positive terminal and this is negative terminal of my diode, okay, and when this negative cycle will pass, okay, it means that in this condition this diode is now in reverse bias stage, okay. So I will just draw it over here, okay. So this is the input signal that I want to measure, okay, and say I am considering that this diode is start conducting for 0 volt only, okay, and not say 0.7 or 0.3, okay. I am considering the ideal case, so that when you have this positive voltage appearing across this diode, means that this diode is in the forward bias condition, and in that case the output, the whole input actually will appear at the output. So this is Vi and this is Vo. Okay, this is the output voltage and this will appear, okay. However, when this input reaches in this negative cycle, okay, you have this diode is now in reverse bias condition, and due to that there is no current flowing and this meter will see actually no current, okay, and ideally it will appear as open circuit and there will be no output in this time, right. So for say this is T by 2 for the time being, okay, and this is T. So till T by 2 you have this conduction and in the other half it is 0, okay, there is no output, and that is why I am saying that the other half cycle of this input voltage is now blocked, okay, and it allows current to flow during only one half cycle of the AC input, okay. So during the negative half cycle the diode is reverse bias and no current flows, okay, and therefore if you see for one cycle it is like this, okay, the same is drawn over here, and then it is blocked and again this is appearing and again this is blocked, okay, means that it is appearing as a pulsating DC. So you have a pulse of DC, okay. Since it is only in one half, I am not calling it AC, rather I am calling it a pulsating DC. So output is a pulsating DC consisting of only one half of the positive waveform, okay. The PMMC meter, okay, the RM meter, okay, will only respond to the average value of this current, okay. So the output DC voltage of a half wave rectifier can be calculated as Vrms is equal to V peak by root 2. We have seen this earlier also, or in this case we are calling this Vm, okay, the peak voltage is Vm. So basically RMS value is Vm by root 2, okay, or the DC voltage or the average value is equal to the V peak by pi, and this value you can simply calculate by averaging this value by 1 by 2 pi from 0 to pi for sinusoidal wave, okay, 0 to pi Vm sin omega t, because this is in the half cycle, and if you integrate this you will get this V peak by pi, okay, and this value is nothing but 0.318 Vm, okay, and this is the DC value that this half wave rectifier is giving you, okay, in terms of the peak value, okay. So this is about the half wave rectifier. Then this half wave rectifier, if you see, is very simple in construction. You have used only one diode, okay. They are low cost devices and the sensitivity is compromised because of this only utilization of only one diode, okay. So and also you have high ripple content because rectification is not complete, and sometime it also end up having some poorer result or accuracy is sometime compromised, okay. Therefore they are rarely used in precision instrument, and mostly if you want to demonstrate a rectifier based instrument they are used, okay. Now the full wave rectifier, particularly the center tapped type, is shown over here. In place of one diode there, it uses a 2 diode configuration, and this is centrally tapped, similar to the center tapped transformer that you have seen, okay. So in this case, by just utilizing two different diodes, you can utilize both the cycle of the AC. Okay. In the positive half cycle, diode D1 is conducting, okay, and in the negative half cycle, this diode D2 is conducting, and one thing is ensured that current through the PMMC flows in the same direction for both half of the cycles. Okay. So output is a full wave pulsating DC. Again it is pulsating, but it is a full wave pulsating, but if you see, this negative cycle is missing, and even this negative cycle is reversed to positive cycle. So if you see, if I trace it, it is basically DC only, but sometime it is going to some high value, then sometime it is coming to some low value, and again if you see, this is a DC value only, it is reaching to certain value and then it is coming to certain lower value and then again going to upper side and then coming back. So kind of pulsating, but for the full cycle. Okay, so it's a full wave pulsating DC. Okay. Now the average and root mean square output voltage for this single phase full wave rectifier is also very similar to what we have seen for half wave rectifier. The RMS value is again V, for the sinusoidal wave it is V peak by root 2 or Vm by root 2. Okay. Or to calculate the DC value or the average value, you have to calculate simply by using this 1 by pi 0 to pi Vm sin omega t into d omega t, and if you integrate it, the average value can be given as 2 by pi V peak. Okay. So or 2 by pi Vm in this case. Okay. So this is how full wave rectifier works. Okay. The AC sensitivity of a rectifier instrument depends upon the type of rectifier it uses. Okay. For a half wave rectifier with sinusoidal input, AC sensitivity can be simply 0.4 times the sensitivity of DC. Okay. And for full wave rectifier with sinusoidal input, the AC sensitivity is just double of that or 0.9 times of the DC sensitivity, and the expressions for this sensitivity are not valid for non-sinusoidal input waveform, say for example square, triangular or sawtooth, but then you have to take into consideration the DC values and then you have to integrate it, and similar to this you have to find the DC component into it and then calculate the sensitivity of that particular kind of instrument. Okay. So this full wave rectifier using this centrally tapped transformer has of course higher sensitivity than the half wave rectifiers and has better accuracy. They have reduced ripple as compared to the half wave rectifier, and they require center tapped transformer, although they are bulky and costly, but then your sensitivity is increasing and you are also reducing the ripple factor, okay, or ripple component. Okay. They are used in some AC measuring instrument, but less common today due to transformer requirement, and then you have other kind of full wave rectifier in place which is known as bridge rectifier, and because of this the centrally tapped rectifiers utilization has decreased. Okay. So this bridge rectifier in place of two diodes utilizes 4 different diodes in a bridge configuration, and by using just 2 more diodes it avoided utilizing any centrally tapped transformer, means the bulky part is now removed. Okay. So that's why this is the most widely used rectifier in measurement or measuring instruments. Okay. So during the positive half cycle 2 diodes conduct, and during the negative half cycle the other 2 diodes conduct. Okay. So if you see this configuration, okay, this is the voltage to be measured between these 2 terminal. Okay. I am calling this diode 1. Okay. This is diode 2, diode 3 and diode 4. They are connected in a bridge form. Okay. Now say I have a positive cycle, or say I have a sinusoidal wave or sinusoidal voltage flowing, I am calling this input. Okay. And this is flowing in this or say some current because of this is flowing, so I am calling this say II. Okay. Is flowing in this bridge configuration. Okay. Now if you see for the positive half cycle, okay, let's see which diodes will be operational. Okay. So for the positive half cycle, this terminal is say positive, okay, and this terminal is negative. Okay. Since this positive terminal is connected to a positive or say positive part of this diode, okay, I am not using the word cathode and anode right now, okay. I am just marking them a positive and negative, okay. So, say this half cycle where you have this positive cycle. So, this positive, this is a just virtual concept I am using, okay. This positive cycle is passing through everywhere, but I am considering this diode 1, and let us see what happened to all these diodes first, okay. So, this positive terminal is connected to positive of this diode 1, okay. So, you can say that this diode 1 is conducting, okay, and in ideal case it is providing a complete path to flow the current, or it is basically short circuited, okay. Now, if you see this positive is connected to negative of this diode 3, okay, because of which what will happen is it is acting as a open circuit, okay, no current is flowing through this. So, I am just omitting this part, okay. Now, let us see what happened to this diode 4 and diode 2, okay. This negative part is connected to this negative of this diode, or say I am just marking all positive and negative, okay. So, this negative is connected to this positive of this diode 4, okay, because of which this will also be open, and this negative is connected to this negative, means it is in the forward bias condition, means it will be shorted. Now, the current which is flowing will flow like, because of this voltage will follow this particular path, right. It will follow this particular path. It will just move like this and will move like this, okay. And this is just in one half, okay, and the output will be like this, okay. Similarly, if you consider this in the negative half, the direction of current will be same, and again you will have this, okay. So, what you are achieving is basically you are again reaching to a pulsating, a full wave DC kind of signal that you have achieved using a center tapped transformer based rectifiers that you have seen, okay. So, therefore, the current through the PMMC remain in the same direction as we have already seen, okay, and it produces full wave rectified output, okay. The advantage of this bridge rectifier is that it has very good sensitivity and accuracy, okay. The size can be compact because you are not using any transformer here, okay, and they can be very good or very efficient converter of AC to DC, because most of the signal you are converting to, you are not wasting the half cycle, okay. They have a slight voltage drop due to two conducting diodes in one direction, okay, and they are widely used in rectifier type AC voltmeter and ammeters, and they are suitable for low level AC measurements, okay. So, if I compare all these different kind of full wave or half wave rectifications, we have seen that for centrally tapped full wave rectifier we uses two diodes, while for half wave we need only one, although it is not sufficient, but some work is done by it, okay, while the requirement for bridge kind of rectifier instrument, the diode requirement goes to even 4, okay. A transformer is not used in the half wave rectifier, while for centrally tapped you have basically you are using centrally tapped transformer, okay. AC utilization is just 50% in case of half wave, while it is 100% for other two full wave rectifiers, okay. Sensitivity of half wave is of course much smaller as compared to the other full wave rectifiers, and that is also reflected in its accuracy. Accuracy of this half wave is poorer, while for bridge rectifier it is very good, okay. And in practical you will find most of the rectifier as bridge rectifiers, okay. Sources of errors can be the non-linearity from the diode, okay. Then again these diodes are very vulnerable to temperature changes, so they are very much affected by temperature, and then you have loading errors and the waveform errors, okay. These instruments you have high accuracies even at lower frequencies, okay. You can also achieve high sensitivity and uniform scale, okay. The device or the meter consume very low power, so these are certain advantages, while there are different disadvantages also, like they have a limited frequency range and the temperature sensitivity is not the great thing that you want in some instrument. So you want your device or instrument to be less sensitive towards any change in the ambient condition, be it temperature or be it humidity, okay. But the non-linear characteristic of the diode is one of the important drawback, because of which this rectifier instruments sees a lot of setbacks, okay. They are waveform dependent, okay. For sinusoidal you have different values of SDC and other things, but for the other kind of say sawtooth or say for square wave, you have all the calculations are different, okay. So you have to design your rectifier instrument in such a way that it operates for that particular kind of signal for which the customer has intended, okay. Applications is enormous. You can use them as AC voltmeters, they can be used as AC ammeters, okay. They are very useful for audio frequency measurements, portable measuring instruments, okay, and for calibration as well, okay. Then this is just discussion on rectifier instrument, but if you see, we are not very clear that how the scale of the rectifier instruments will look like, okay. And why we have not discussed this scale, because there is one term which is known as form factor, and the scale of the rectifier instrument is greatly influenced by this form factor of the rectifier, okay. So the form factor, if you see, it actually relates the RMS value to the average value, okay. And in general, if I have to define the form factor, I am using a term Kf to represent this form factor, can be given as a ratio of the RMS value of the sinusoidal signal by the average value of the sinusoidal signal, okay. So the form factor can be particularly for the half wave, or say let us see for the full wave, okay. Form factor can be given as the RMS value that we have already seen as Vm by root 2, okay, and the average value we have seen 2 Vm by pi, okay. If you solve this, you will get a value of 1.1, okay. So form factor for full wave rectifiers is 1.1, okay. Similarly, if I have to calculate for half wave rectifier, okay, I will just remove this 2, okay, and Vm by pi is what the average value was there for half wave rectifier, and the form factor is Vm by root 2 by Vm by pi, and by cancelling this Vm, okay, I will get form factor as 2.22. So the form factor for the half wave rectifier is just double of that of full wave rectifier, okay. So this form factor carries lot of importance, particularly in the scale design of the rectifier instruments, okay. So we have seen that the rectifier type measuring instruments are calibrated to indicate the RMS value of the sinusoidal voltage or current, and these instruments inherently respond to the average value of the rectified waveform, okay. So what you are doing is rectifiers you are using in this instrument in the intermediate stage. You have seen this, okay. You had rectifier and you had input in the form of say AC signal generator, okay, and then you have a PMMC for the measurement of the pulsating DC, okay. So this rectifier type measuring instruments are calibrated to indicate the RMS value of the sinusoidal voltage. These instruments are inherently respond to the average value of the rectified waveform. To ensure that the instrument indicates the true RMS value for a sinusoidal input, appropriate scale calibration factors are applied, okay. So for instrument employing say a full wave rectifier, the scale is calibrated using the multiplying factor of 1.11, okay, which was basically the form factor or the ratio of the RMS value to the average value. Similarly, for instruments which is very rare that we have seen, okay, employing just a half wave rectifier, the scale is calibrated using a multiplying factor of 2.22. Okay, so basically this multiplying factor is nothing but the value with which you multiply the actual scale of a rectifier instrument, okay, and these multiplying factors compensate for the difference between the measured average value and the actual RMS value of the sinusoidal signals, okay, and that's how you compensate for these changes, okay. So I think this is more than enough to understand a rectifier type of instrument, okay. Then we will have in our next week, we may discuss about different instruments again, because next week is also the next week is also part of our module 2, which is the analog meters. Okay, and till now we have confined ourselves to the measurement of current and voltages. However, now it's time to expand, and from the next week we will talk about measurement of various other quantities, including the measurement of resistance, measurement of power, measurement of energy, frequency, as well as, if the time permit, we'll also see measurement of phases. Okay, so with this portion of analog meters we have finished. Thank you.